Good morning. This is Pete Skinner. I'm an engineer and scientist from the USA, actually from New York State. That's in the northeast part of our country. I install and design solar thermal systems and heat pumps to meet all kinds of different demands. Lately, I've been focusing on the net zero multifamily market, where there's a need for solar to make up the difference between the load and the energy required to meet that load. So as an engineer, I work with solar and other mechanical systems and have published a textbook called Solar Hot Water Fundamentals. And based upon that, not only do I build my systems, but I also do instruction around the Northeast America. I've come to Eurosun because it's the best place to learn about the advances in solar thermal technology. The very best professionals in this area and researchers gather each year to discuss the issues, and it's a great honor for me to be a presenter here, at least as far as my poster is concerned. The poster you see here describes my topic today, which is how to optimize a solar hot water system by adding heat pumps to the design. Heat pumps, as you know, gather heat from its environment, either from the ground or from the air, and thereby manage to create heat at a higher level at a very favorable coefficient of performance. By having a higher COP, as we call it, you use less electricity, and therefore you need less from the power wires or from your photovoltaic systems. So it's a win-win if you can install a heat pump that makes a difference. As you can see in this poster, here is a net zero apartment complex with panels that I installed on top, 13 buildings, 26 systems, and they're working very well. But they didn't have a heat pump. The new development, not far away, is going to have the same systems, only with heat pumps. I wanted to show my client that by adding the heat pumps, the extra cost would be more than made up by having fewer solar hot water panels and fewer PV panels. Now, I knew that to be true in my heart, so to speak, but I needed to show it. It took me a couple of years, actually, of thinking how to do this, and just recently I had a breakthrough. And that breakthrough is represented on this graph. I ran the Swiss solar simulation program called PolySun many, many times for a different number of panels. On the x-axis, you see 8 to roughly 24 panels. Each one required a separate run of PolySun. I also ran it with the heat pump and without the heat pump. In so doing, you can see here two sweet spots. A sweet spot for the heat pump backup and a sweet spot for the no heat pump backup. These two sweet spots show a designer how to, as we say in the United States, how to right size your array. Instead of building an array with 24 panels, which is expensive, I have shown here that by adding a heat pump, you can reduce that number from something like 18 to something like 10 to 12. This reduction in the number of expensive solar thermal panels saves money, and that makes clients very happy. Now, in order to do this work, I work closely with PolySun here in Switzerland to make sure that their program was best fitted to my particular design. But I didn't stop there. I was very fortunate to meet a graduate student by the name of Amir Zareh from Iran, who is working now at the University of North Carolina. He offered to do a separate model based on Trinsis. Trinzus is probably the gold standard on simulations. He did one using the same design as we used at PolySun and came out with very similar numbers. But not only similar numbers, but he was able to do this on time steps of 3 minutes. The PolySun model was run on 1 hour time steps. So consequently, we've got a very time-specific performance analysis here, which you can see in these graphs, both in terms of the way the solar pump turns on, the way the heat pump turns on, and the way the backup electric elements come on. We resolve this in PolySun in a diagram here that shows the energy inputs here and the energy outputs there. And you can see very easily that the sun provided the bulk of the heat and the heat pump the majority of the backup heat. There was some additional contributions for the electric elements because sometimes the air is so cold that it is inefficient for the heat pump to provide the backup energy. However, that brings up one final thing that I should mention. There are two types of heat pumps that are popular in our region. One is the Geo Heat Pumps, which are based on wells in the ground, and the other is an air-to-water heat pump. The air-to-water heat pump takes heat out of the air. The Geo Heat Pump takes heat out of the dirt. The problem with the latter, the Geo system, is that it's expensive. To drill the holes and install all the pipes and the pumps is an expensive proposition. By using the air-to-water heat pump, it's self-contained, comes in a box, you put it on a pad, and you connect it to the tanks, as you see here, with the heat exchangers inside. It's relatively easy, and as a result, makes this kind of an install cost-effective. So what did we learn here? The bottom line is with this graph, and by running the Trinzus model and the PolySun models, we showed that you can, by right sizing your designs, minimize the number of solar hot water panels and minimize the number of PV panels necessary to provide the electricity for the heat pump, and thereby save money for your clients and build the very best system you can to meet our needs for sustainable energy.